Real quick for anyone joining us that's absent today, period 1, no one's absent, maybe period 6. We did go over our forever cards, so go ahead and check them out online. This is the one card you might not have gotten this piece down on, but get those updated because we need to be memorizing some of these rules. Okay, what'd you guys do in your workspace at the beginning of class? Solve this guy.
I reintegrated.
Okay, integrated, meaning?
Plug in B minus A.
No, not yet.
Oh.
We have to
Find the antiderivative first. You have to find capital F for the antiderivative. So what's the antiderivative of this guy?
X squared.
What's the antiderivative of this guy?
Secant X.
And it's a positive secant, but there's a minus, right?
No.
Am I going to put a plus C?
No.
Because what happens every time I go plug it in bounds to the plus C? Good. We're just saving time. We're just saving time. Now, why did I write the pi over 3 and a 0 again?
Because you haven't plugged in your B minus
I
A.
haven't plugged in. Good. So it's plug in top minus plug in bottom, right? Top minus bottom, or f of b minus f of a, where b is the top one. Always, always. So when I plug in, we end up with pi over 3
squared.
or pi squared over 9.
Minus 1 over
Minus?
cosine. Minus 1 over cosine pi 3.
That's probably the easiest way to think about it, because Sean is like, hey, I know cosine better than secant, so that's not a bad idea. Secant's 1 over cosine. But that was just f of b, right? What else do I need?
Squared minus 1 over cosine.
What's 0 squared?
Just 0. A lot of people get used to plugging in 0 becomes 0, but the problem is, kiddos, what's cosine of 0? 1. So we have to be careful, because there was a piece that came from f of a. And then over here, I end up with pi squared over 9. Or you could have left it, pi over 3 squared. That's numerical. This is now numerical.
Minus 2.
This is a bit of a struggle. 1 over, pi over 3 is a 60, yeah?
So 1/2.
Over a little, up a lot. So you have 1/2 is the cosine. Root 3 over 2 is the sine. We're choosing the 1/2. Could you flip it to make it 2? Yeah. Could you box it and say, whew, the numbers are there, I'm done? Also good. The other answer, if you had fully simplified, like what would have been in the back of the book or what would have been a multiple choice, the answer would have been minus 1. But if it was a long answer, stop there. Done, 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 done. Questions on the process? Antiderivative. Plug in the bounds, and in what order?
B minus A.
And then A. F of B minus F of A, antiderivative of B minus antiderivative of A. Or plug in the top minus plug in the bottom. Now, what was going on with this guy on Friday, and why was he special?
Because it's
Absolute. And so the original graph of just e to the x minus 1, forget the absolute value, did dip below the axis. We could actually find where it dipped below by finding the 0. And we found the 0 to be at 0, and actually without a graph at all, we could have said, okay, let's plug in something like, on one side of 0, let's plug in 1. Kiddos, what's e approximately as a number?
2.78.
Good, 2.71828, but 2.7-ish, right? If I plug in 1 or 2 or 3 or 4, is this going to be a positive or a negative value? Positive. So we know the graph is going to be positive for x greater than 0. So positive stays the same. And then for x less than 0, if I plug in negative 1, wait a minute, what's negative powers do?
1 over. So
1 over. So 1 over 2.7-ish, or 1/2-ish minus 1, that's a negative. So we know you don't necessarily have to have the graph. You could have plugged in values below 0 and above 0 and saying, he's the in-between, he's the 0, so who's who? What did I do over here? Once I figured out that half of the graph, or a part of the graph, is going to flip signs because of the absolute values,
you
the negative
just
values.
separated.
I separated to look at them separately. The region from 0 to 1, the positive region, and the region from negative 1 to 0, the negative region. But what else did I do?
You had to make the first region negative to flip it.
Now here's the snazzy thing. If I was to actually plug and chug, wait a minute, some of you guys are like, hey, I should anti-derive, right? Okay. What's the antiderivative of e to the x minus 1?
E to the x minus x.
If we were to, for instance, not remember this part, or not even think about it, and we did a good job of splitting up, couldn't we technically have plugged in for the first piece? And when we plugged in, we would have gotten e to the 0 minus 0 minus e to the negative 1 minus negative 1 Then we would have gotten, what's anything to the 0 power?
1.
1. What's 1 minus 0?
1.
Okay, so that's just 1.
Minus.
Minus,
What is it?
now we have 1 over e minus 1. Here's my question. Is this a negative value or is it a positive value?
Negative.
Yeah, because the 1 minus 1 is going to cancel, right? And I'm going to be left with a negative 1 over e. Now that's only this first piece. I still have to do the other piece, or I'm going to do the e to the x minus x
This D.
from 0 to 1. And I'll come back to that in a second. Hold on, Tyler. I'm saying, what if we forgot this? Give me 1 second. And we just solved it like normal. We would notice, hey, this is a negative, but why is that bad in context of the problem? Why is it bad to have a negative area?
Oh, because then when we do the other area, it'll be 1 over e, and then area will be 0, and we know that we have a full area.
That's one way of looking at it, is that when we add the next one, which is going to be a positive, it's going to take away. I think that's a little bit more convoluted than I was thinking of. Let's go a little bit more simplistic. Why is it bad to have any sort of region of this function be a negative?
It's an absolute value.
Yeah, the negative doesn't make sense. But is the number good? Yeah, the value is great. It's exactly right. What's wrong? The sign, because we ignored the absolute value when we solved. So one way is, if you know what the graph looks like, or if you know by plugging in values less than 0, it'll be a negative. The value will naturally be negative. We say, well, we need to make this the opposite sign. That's one way. We could put the opposite sign in there and be like, okay, let's make the negative the negative. That's one way. But what's another way of doing that?
Absolute value.
Yeah. Once we split up the bounds, another way, instead of just putting that negative in there, which is not bad, but we could just say, you know what, forget this whole who's negative and who's not. I'm just going to solve it like normal after splitting up the bounds and say, hey, whoever the answer is, I need to make him a positive. And I could do that to both pieces and say, I don't even need to think about who's not positive or who is positive. Let me just solve it and look at them and say, hey, are you a positive or a negative? Now, careful. The absolute values, if you put them on the outside, do not affect anything until the final answer. You still need to do f of b minus f of a. You still have to do that subtraction in the sense of realizing this is one full function whose antiderivative needs to be solved with FTC. What I'm doing is looking at the final answer and saying, I like that number. I need it all get in between subtraction. But right now, if it's a negative, it needs to flip to become a positive. And then over here, when I solve, we could put absolute values and play dumb and be like, I don't know what the graph looks like. I don't know what's going on. I just know it's absolute value. So this is our way of kind of playing ignorant, but not in a bad way, in a way that we're just simplifying the process. E to the 1 minus 1 minus e to the 0 minus 0. As we already talked about, this is 1. E to the 1. There we go. It's just e. Minus 1 is minus 2. Now, this is a little bit of a struggle, but kiddos, do I need to flip the signs of anything? No, because what's e? 2.71828 minus 2, that's a positive value. So I'm just going to leave it and say, okay, keep the e minus 2. Don't change it to a plus. I would put them together if I could, but they're decimals. I'm not going to do that. I'm just going to leave it. So I'm going to go ahead and say, let's go ahead and finish this puppy off. And to finish him, I changed this little negative guy that came from this whole left-hand side to be a positive 1 over e plus e minus 2. I guess we get common denominators, blah, 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 but we'll just stop there.
If you left it as absolute value bars, would the AP be okay with that or no?
Not if it was a long answer. And if it was a multiple choice, they definitely won't leave it with absolute value bars. If it's a numeric answer. If it's like with a variable, then you're stuck. Okay, so that was the process. Could we get a graph? Could we think about values? Could we figure out exactly which one flips? I suppose. But could we just split it up? Take absolute value of each of the different pieces, saying, I don't know, one of you probably stays the same and one of you probably switches. Wait until you do all the f of b minus f of a and then look and say, oh, you're bad, flip. You're good, keep. Done. So let's make it a forever card. Ready? Handling absolute value. Oh, come on. I already showed this forever card to you. Handling integration with absolute value functions.
With every...
That was sneaky, Mr. E, just sneaking in.
Schnicker schnicky, yeah, but we figured it out first. Isn't that cool?
True.
Be ready. Split up the integral using the x-intercepts, aka set the y equal to 0. So when you have, for instance, the integral of the absolute value of f of x dx from a to b, we set the f of x equal to 0. Figure out when that happens, which could be just once, or it could be more than once. And once we figure this out, once we split it up, then we go ahead and say, all right, let's take them from a to c of the function, absolute value of the whole thing, plus, now it's time to go from c to b of the function, absolute value. And then we solve like normal. So split up the integral using the x-intercept, setting y equal to 0, aka take the inside of the integrand, or I should say the inside of the integral called the integrand. Take the inside of the integral, set him equal to 0, see if there are any zeros in between the bounds. You don't have to worry about if it's outside of the bounds, only if it's in between the bounds.
They're moving around too much.
I know, I apologize. I'm getting in there though. There we go. I think I just do 2. That looks kind of lame. Let's do 3. That's better.
Wait, what's 36?
36 is FTC, Fundamental Theorem of Calculus. That was the one from Friday?
Oh no. Oh wait.
Oh, no.
Oh no. Wait, what number is this one?
37.
Oh my gosh, I'm missing 2.
Oh, wait. Well, you know, write them in.
No. What, I think 36 was, wait, 30, oh.
36 was FTC. It was a new one. That's
Oh,
all right,
yeah,
though.
okay, well 36 will be after 37.
That sounds good. As long as you have it. The order is helpful as far as us referring to the same thing at the same time, but besides that, the point is that you get them in.
Except I already labeled this one 37, so.
Yeah, hence the 36 later. Unfreeze.